an official stream. I just want to make sure everything's working and get started with some little coding and make sure that my chat box and everything will show up. Oh yeah, I got to put my chat box on this scene as well. Give me a second. There we go. Chat box. Chat box. Excellent. Working. All right. So the point of KittyCoding is that I am obviously a cat. This is just the default cat that comes with YouTube Studio. But it's still it's fun to code as a cat. And all of these assets are kind of placeholders. They're just generated stuff, but it's enough to get me started today. Okay. I'm just going to jump right. Oh, I forgot to start my music. Excellent. I'm on the ball today. On the ball of yarn. Meow. Meow. There we go. Got some chill music going. Wow. All right. Okay, now it's time to do some coding. Let's go. We're going to transition to our browser scene. Get my kitty face out of the way of all this. Down in the corner here. There we go. Whoa, infinite mirror effect. What's happening? Okay. I'm going to switch to my LeetCode screen. Now on my LeetCode screen here, you can see, hold on. Oof. Come on. Okay, on my LeetCode screen, you can see this is my LeetCode profile. This is a website for doing little coding challenges, the kind that you will see on like coding interviews and that kind of stuff. And we're just going to do some really easy ones today to get started. So if you have any particular problems you want me to solve, you can go ahead and let me know in the chat. Drop a link or let me know the name of the problem and I can take a look at it. In the meantime, I am just going to pick a problem at random. Something easy. So the first easy problem that pops out at me is this TwoSum problem. Hopefully you guys can see clearly. I'll make this text a little bit bigger just in case. TwoSum. So TwoSum is one of their easiest problems. I'm going to click on TwoSum. All right, so first we're going to go through the description. And in all these, it is really important that you read the description carefully because there's a lot of like subtle details that aren't just in the initial problem description. So for example, in this case, it says, given an array of integers and an integer target, return indices of two numbers such that they add up the target. So this is a little clearer if we look at the example, what they're saying. So here we have numbers 2, 7, 11, and 15. And we have a target of 9. And if you look through these, you're like, which of these two numbers adds up to 9? Well, 2 and 7. Those are the two that add up to 9. There's no other possible answer. In fact, they define here in the statement that every input has exactly one solution. So you don't have to worry about there being multiple solutions or no solution. That's just not going to happen. And then it also says you can't use the same element twice. So an example of this you can see here is you have 3, 2, and 4. So you would think you could just choose the 3 twice and that would get you to the target of 6, 0, and 0. But you're not allowed to use the same element twice. So you can't do that. That's something you have to look out for. But if it is the same number at different indices, like here, these two 3s can add up to 6. That's allowed as long as they are at different indices. So these are all important to remember, especially as we look at the more optimal solutions. That's very important. All right. Meow. First, I'm going to look at these constraints. So these constraints are important because this tells us how much we have to worry about things like integer overflow. In this case, they're telling us all the numbers and the target are between -1 billion and 1 billion. So they can be negative, they can be positive, but they don't get right up to int max, which is like 2.1 billion roughly. So that helps protect us from some of those overflows because even if we subtract 1 billion minus -1 billion, we still get 2 billion, and that's still in range. So that makes our lives easier. There's so many boundary cases with overflow that it's better if you don't have to worry about it. Okay. It also tells us that the list can only be up to 10,000 elements. And that's helpful as well. Although it does mean that the really efficient solutions are not really even that necessary on problems of this size. But the advantage is that we don't have to worry about weird like memory issues or like the data transfer problems with caching or anything like that. It's just going to be a fairly small list. We also don't have to worry about list with less than 2 elements, meaning the empty list. So it's like, what do we return if the list is empty? It won't be empty. That's good. Okay. And the follow-up after we're done, they'll ask us if we can come up with a more efficient algorithm than the most obvious one. So I'll come back to that. So now we've reviewed the whole problem. And I'm going to do the simplest possible solution. So it's always a good idea to just start with the easiest solution you can think of. So I'm writing in C++ here. I'll probably do this in Python as well after I do it in C++, just to show you. So I'm just gonna do a loop through the array of nums. This is a very standard for loop. Should be no surprises here. Doing a little copy paste to save time. And now all I have to do is check if nums I plus nums j is equal to the target. And if it is, then I can return a vector of I and j. So this solution is not going to be correct, and we're going to see why. So I'm going to run. Whoops. So first of all, it's telling me non-void function does not return value in all control paths. So it's like, hey, you told me what you return here, but what do you return if you get all the way to the end and you haven't returned anything? So the answer is that can't happen because it says exactly one solution. This would only happen if there are 0 solutions. So we could just we could return anything we want because we're never going to get here. We could put like 0, 0, or we could put -1, -1 or whatever. But I'm going to do something a little better, which is we can type assert false. Assert false says if the execution ever gets to this line, the program will abort with an error. And this actually also tells the compiler, if the compiler is smart enough, that control flow cannot get here. So we don't have to return anything here because this is impossible. So now I'm going to hit run. So we got the correct answer on this first case, which comes from example 1, where we saw 2 and 7. And it found that the target is 9. And it got an output of 0 and 1. So that's index 0, which is 2, and index 1, which is 7. Those add up to 9. So that's correct. But then when we got to case 2, 3, 2, 4, which is from example 2, this one is actually incorrect. And we said the answer was 0 and 0. So we said index 0 is 3 plus index 0 is 3. But remember, it says you may not use the same element twice. So we forgot about that. In order to fix that, we're gonna do I is not equal to j. And if we add this condition that I is not equal to j, that makes sure that we never use the same element at the same index twice. So we're gonna run it one more time. You can see now case 2 is passed. We get the same answer as in the example, 1 and 2. So the 2 at index 1, the 4 at index 2, they add up to 6. And in the third example, 3 and 3, you can see we got index 0, which is 3, index 1, which is 3. We're allowed to use the same number twice, just not the same index. So if this were 0 and 0, that'd be wrong. But if it's 0 and 1, 2 different index 3s, that's totally fine. So we got all these cases right. So let's see if we can submit this, because I think it's correct. Let's find out. It is correct. It was accepted. And in terms of speed, we have beat 8.37%, which is not very good. You can actually see here are the fast solutions over here. Whoops, I did not mean to click on those. So here's my solution. 172 milliseconds is how long it took to run on all the test cases. And you can see I'm taking way longer than these other solutions down here. So that's no good, especially in C++, which I thought was a fast language. Mrow. But apparently not. So Instead, we're going to figure out a way to make it run as fast as some of these other solutions. Why can I thought if I clicked on my own solution, I would see it, but I don't know. Here we go. Okay, now I'm back on my own solution. I'm going to close these code samples. So next step, I have to figure out how to do it faster while still remaining correct, because this solution was correct. Let's see what happens if I click Analyze Complexity. This is a new feature, I think, where it will tell me what it thinks the complexity is. It thinks my complexity is n squared. So that's not great. Although it totally makes sense if you think about it, because here we have two nested loops. And for each instance of the nested loop, we do a constant amount of work in the middle to test if it's a solution. So the first improvement we can do to the runtime, and this is one of the easiest things to do, is just to say, like, so here we're testing every possible combination of indexes. So we're testing 0 and 0, and then 0 and 1, and then 0 and 2, and then 0 and 3, and then we're testing 1 and 0, and then 1 and 1, and then 1 and 2, and then 1 and 3. So in particular, we're trying I equals 0 and j equals 1, so that's the 2 and the 7. And we're also trying I equals 1 and j equals 0. But as you know, addition is commutative, so we don't have to try both of them. If one of them works, the other one will also work. So instead, we can just start j at I plus 1. And this will actually make sure that j is never equal to I, because it starts at this number, which is bigger than I. And it will also make sure that j is always bigger than I, which means that we don't ever have like I equals 1 and j equals 0. So we can avoid that. This will visit each pair once, so 0, 1, 0, 2, 0, 3, and then 1, 2, 1, 3, and then 2, 3. So we're reaching each pair of numbers once, and we never look at the flipped version where they're the other way around. So that's what we want. And that means we don't need this I is not equal to j anymore, because that can't happen. So here we go. We're going to give it a run. Meow. Excellent. So as you can see, we have passed all the test cases. I believe I can submit it. Now let's see, our runtime currently is 170 milliseconds. Let's see if that goes down. It did. It went down a bunch. 53 milliseconds. Now we're in this big cluster right here of solutions. So we're going a lot faster now, and that's good news. So the question is, and I'm currently beating 90% of solutions, which is, on memory, because I'm using very little memory here, just the bare minimum. And I'm beating 27% of solutions on runtime. That's not very good. So instead, I'm going to, what can I do here? So there's a lot we can do to improve the complexity by noticing that here we're still looking at basically every pair of numbers. We avoided some of the pairs we didn't have to look at, but we're still looking at a lot of different pairs of numbers. So there's a trick that we can do here to try and avoid this. And the trick is to notice that, say we're looking at I equals 0 and we're like 2. One number is 2 and then the target is 9. Okay. So the question is, if one of the numbers is 2 and the target is 9, then we already know what the other number has to be. It has to be 7. So it's kind of silly to look at these and be like, is this 7? Is this 7? Is this 7? Like, why don't we just remember where the 7 is ahead of time by creating another data structure to help us remember? So that's the idea of how we're going to make it faster, is we look at the 2 and then we ask, hey, other data structure that we constructed earlier to help us, where's the 7? Tell us where it is. And then we can use that to jump directly and find the index of the 7. So to think about what kind of data structure we need here, anytime you want to take an array and invert it so you can take the value and look up the index instead of taking the index and looking up the value, the way to invert it is to use a dictionary or a map, as it's called in C++. And so I'm just going to use a map. And my map is going to map from an index, or rather a value, which is always an integer here, to an index in the array. And actually, if we look down here, you can see, hold on, not here. In the description, it actually tells us that the list can never be more than 10 to the 4 elements, which means that technically this int could be a short, because a short can only get up to about 65,536, and this only gets up to 10,000. So I could put short here instead of int, but I'm just going to do int for now, keep things simple. Let's see. So this will be value to index. And now we're going to go through our array and we're going to prepare this data structure. So at the beginning, it's empty. We're going to prepare it. We're going to say value to index, pushback, or sorry, not pushback. This is not an array. We're going to say that if we look up by value, which is num's I, we will get the index, which is I. So for example, in this test case here, we would first do value to index of 2 equals 0, value to index of 7 equals 1, and value to index of 11 equals 2, and value to index of 15 equals 3. So there are some edge cases to worry about here, which I will talk to you about in a minute, but this is the basic idea, and we're going to go ahead and implement it and see how it goes. So now that we've constructed this map, instead of having this J loop, which will search for the matching number to get up the target, we can just jump directly there. And the way we're going to do that is we're going to do a lookup. We're going to do a find where we say, so I'm going to do this in the simplest way first. I'm just going to say if value to index, find, and what is our value that we want to find? We want to find, let's see, other value is going to be target minus num's I. And then we're going to look for other value. And if we find it, if this is not equal to value to index.end, in other words, if it exists in the array, it doesn't always exist, but when it does, it'll tell us the index. So then we can just say, well, now we know what J is. J is just going to be value to index of other value. And we can go ahead and return I and J, just like we did before. Boom, there we go. So this is the basic idea. We construct value to index, which will reverse this array so that we can look up, take the value and use it to look up the index. And then we're going to go through the numbers one by one, and we're going to look for their matching number, their soulmate. Soulmate. In other words, if we have 2 and the target is 9, we're going to look for 7 and figure out what its index is. If the value was 7 and the target is 9, we would look for 2, figure out where 2 is. And if it were 11, well, we would need a -2 to reach the target, and we would look for a -2. There isn't any -2, so we would skip that one. So this is basically how it works. And I can actually step through this code with the debugger to show you some idea of how this works. Debugging. This is a relatively new feature in LeetCode. It's really handy to have debugging. Okay, we're going to step over. So first we're going to set up our map. Our input here is 3, 2, 4. And it looks like our target is 6. So this is the second example. So the first thing it's going to do, num's I. Let me add a watch for this. Num's I. What is this? This is nonsense. Mrow. Why would it do that? All right. This is clearly not looking things up quite the way I intended. But we know that I is 0, num's I is 3. And so we're going to map 3 to 0. That's what we're going to do. And you can see now 3 has been mapped to 0 in value to index. It actually prints this in a really nice way, which I appreciate. Then we're going to map. So 3 has been mapped to 0, 2 has been mapped to 1, and 4 has been mapped to 2. You may notice this is not the order that I set this up in. Dictionaries don't really have an order. They basically end up getting ordered Yeah, we're gonna do this. This is essentially constant time if we are using a hash map, because each index is going to be constant. Thank you, Elemental Magic Card Game, for joining. If this were like a red-black tree where the lookups and insertions are more like log n time, then this is going to be like an n log n solution. So this is how it works. So now that we have this mapping, then we can go here, and in this case 3, we need the other value to be 3. So we're going to look for a different 3 in the map, and we're going to see that there isn't one. So we're going to skip over to the next index. Now other value, hold on. So now I equals 0, j equals, hold on. Other value is 3. Oh, and I have to also make sure that I is not equal to j, of course. So we have just found a bug. So, and there are some other edge cases to worry about here, which I'll talk about in a minute. But for now, let's just make sure I is not equal to j. And then we'll run again until we get here so I can show you what happens. So I'm going to run into the debugger. I should probably actually get that out first. Okay, I actually need to compute j before I compare j. So if I is not equal to j. All right. I may not entirely always be paying attention to what I'm doing. That's fine. Mrow, I'm just a cat. All right. So now you can see I equals 1, which means other value. So we started with this value 2, and then we computed the other value to get to 6 has to be 4. And then we used our array here to look up 4, and we found it was at index 2, which means that j has to be 2. And then we return I equals 1 and j equals 2, and that's the answer. So this is how it works. And I'm going to go ahead and run this. And you can see it does all 3 of these test cases correctly. I want to pay special attention to the third test case because it's a little bit tricky. In the third test case, when we compute the other value, it will tell us that, let me just show you. So we're going to hit the debugger here. And you can see that it computed, hold on. How do I tell the debugger what I want to use as my input? That's the question. Oh, I can just put it in here for the inputs. Inputs? Debugger? I don't know if the debugger will allow me to change the inputs and the target. I haven't used this debugger a lot before, so this is kind of new to me. But let's just kind of walk through the third case here. So imagine the input was 3 and 3. Then I would say valued index of 3 equals 0. And then I would say valued index of 3 equals 1. In other words, my end result, let me write that out. Value 3 equals 0, valued index of 3 equals 1. And the problem here is that I end up with, it's mapping 3 to 1, but it lost the mapping of 3 to 0 because a map can only map a value to one output. So the question is this okay? Is this really okay? Is this going to break everything? And the answer is actually not, because we're going through the array in order. The index that will get mapped will always be the last index where the value occurs, which means that if the same value occurs twice, it will be the final index where it occurs. And because there can only be one possible solution, that means that, let's see, how do I explain this? So imagine in a case like this where you have 3 and 3, this will be set to 1, which means we start at 0, we find the first 3, then we look up and we find the second 3, and then that works fine. And in any case where you have 2 of the same value being used, and that's your solution, that will work fine. If you have a case where, for example, imagine this was 4, 3, 3, and the target was 7. In that case, there's actually two solutions, 0 and 1 and 0 and 2. Now this can't actually happen in this case because they told us in the description that each input has exactly one solution. So this will never happen, but if it did, we would return 0 and 2, and that's a perfectly valid solution, just like 0 and 1. So there's nothing wrong with that. So really this all works out as long as this, in fact, if we were going backwards through the array here, like if we reverse this loop, it would actually give us the wrong answer, which is interesting. So let's say we go through the array backwards. We're going through this array backwards, which means now we're doing nums, or valued index of, on this 3, 3 example, we would do valued index of 3 equals 1, and then we would do valued index of 3 equals 0. And then we would start at I equals 0, and we would look up where the 3 is, and we would find that j is also 0. And that would be wrong. And so in this case, we actually, we would actually get the wrong answer because we would get I equals 0, j equals 0. This would not be true. It would fail this if check, and then it wouldn't find any solution at all. It would say there is no solution, and then we would get an array here. So I can actually show you this. If I go ahead and try and run this on the test cases. Why did output 1, 0? Hold on. Oh, I see. So in this case, it actually went to the second element and then it found a solution with the first element. So it ended up being correct, but yeah, you have to watch out for these cases where a map has values being overridden. In this case, I think it's okay, but you do have to think about it and really walk through those cases and make sure everything's being covered. So I'm going to go ahead and run this, and then we're going to submit it and show how it's being run in a shorter runtime. So you can see our runtime is now 18 milliseconds. We're beating 48% of other submissions, which is good, but it's not the very, very best. We are being accepted, which means we passed all the hidden test cases, which is good. And if we analyze complexity, it tells us our complexity is ON, which is good. So the first reason that this might not be quite as fast as we thought, I think this map is actually by default in C++. C++ maps are actually, so they follow a specific order, which means that they always keep track of the keys. The keys are sorted using the comparison function, which means that they have to use some kind of tree data structure to represent them in order to maintain this ordering. Like strictly speaking, they're not required to use a tree, but practically speaking, if they're not using a tree, it's really hard to keep track of the key, to keep the keys in order so you can iterate over them in order. So if we want to be faster, then we want to use hashmap. Hashmap doesn't care about keeping things in order. Hashmap was added to, so it was added to STL, I believe in a more recent version of C++, and I think it should work here on LeetCode. Let's go ahead and give it a try. So because it doesn't worry about keeping the keys in order, that allows them to optimize it and make it faster. So let's try running it. Oh no, we have no hashmap. Can we please have hashmap? I'm begging you. I'm gonna try and include it and see if they'll give me hashmap. Okay, so there's a hash map, and I'm going to pull in hash map. GNU CXX hash map. Okay, it looks like we don't have a standard hash map in this context. And if we look here, you can see, oh, why did I say hash map? I meant unordered map. I'm not totally up to date. Hold on, mute. There we go. Okay, so in more recent versions of C++, you want to use an unordered map. Unordered map doesn't care about keeping the keys in order, which allows them to use more efficient implementations, like a hash map, like a hash table. I'm going to give this a run. We see we pass all the test cases still. If you're not really caring about the order of the keys, if you're not iterating over the container and depending on the order of the keys, which we're not doing here, then it's not going to make any difference whether you use a map or an unordered map, except with respect to runtime. So we're going to submit. This should work exactly the same. And you can see we're now at 11 milliseconds and we're beating 63% of submissions. So this is doing a little better. Now the question is, what else can we do? Let me think about this. So I want to be able to beat all the submissions. I want to be able to beat even these solutions that use like 1 millisecond. So the question is, how are we going to do that? One thing we can do is to notice that there's often a crossover point. So this solution we have here, the linear time one, is really good for really long lists where you don't want to iterate with a double nested loop over the entire list because it's way too slow. But if we want to, if we have a smaller example, like if it were just one of these little cases with just 4 elements, then constructing this unordered map and then doing all these lookups is actually like really expensive, because we could have just looked at these 3 numbers and been like, is this 7? Is this 7? Is this 7? Done. We didn't have to be like, well, let's compute the hash of the value 7 and then index into this data structure and allocate all this memory. And it's like, we don't have to do all that. Not for a little list like this. So I don't know exactly where the crossover is going to be in terms of kind of which one works for a small list and which one works for a big list. But I'm going to guess. I'm going to guess and say if nums.size is less than, let's say, 10. 10 is a good guess. So if it's less than 10, then we're going to use our earlier solution. If it's more than 10, we're going to use our later solution. So I'm going to go back actually to look at some of my earlier solutions so I can go get it. Let me see. How do I go back in time? There's some way to do that on this site. Previous submissions. Solutions accepted. Let me see. Submissions. There it is. Okay, here's all my submissions from the past. So I'm going to make sure I don't lose this. And I'm going to go back into the past to my very first submission. So this one was no good, but this one had the doubly nested loop, and it was very, very simple. And so I'm going to take this one back into the present. And I'm going to use it for my small list. I don't know if this is going to work. I am trying this all in real time. We're going to find out. That is my partner, Goddess Calyptra. Thank you for visiting. She is asking if I can visit tonight. And I am just letting her know that I will come see her if she wants to tonight, in which case I will wrap this up pretty soon once I finish this problem. Meow! That's me. I'm the cute kitty. Okay, I'm going to wrap up this problem. First, we're going to see if I try and use this solution for the small problem, and I try and use this other solution for the larger list. Let's see how that does. First of all, is this correct? It is still correct. That's good. If I submit it, how did I do? Let's find out. Whoops. What am I doing? No. I'm going to go. How do I scroll this list? Oh, I just got to do like this. Okay. Description, solutions, submissions. Hold on. Debugger. I know I submitted. Oh, I just have to click on it. Where's my... I want to see how I did on times. I'm a little confused by the LeetCode interface. I might need some training. Meow. Meow. This is fine. This is fine. I'm just going to submit it again. Why is this? It's not showing my solution anymore. It was comparing, you saw before how it was comparing my time to the other solutions that were submitted. But it's not doing that anymore. And I think there's just a button I have to click here. Where is the button? Okay, give me 1 second. Solutions. Submissions. Editorial. Oh wait, I just have to scroll down here. Put this accepted back over here. There we go. So how did this do? I got 49% this time. So it looks like that wasn't actually faster. That makes me sad. Sad kitty. I will try adjusting this. Maybe if I try adjusting this parameter, I can get something a little better. Let's try adjusting this down to 5. And see if that does better. 49%. Okay, I'm up at 59%. But what was I at here? So that's 12. This is 12. This is 11. When I did... Got it. So when I did 11, I was beating 62. So I guess this idea of breaking into 2 different cases wasn't really working out for me. Now you might ask, how could it possibly be slower when I was just breaking into these 2 cases? The answer to that, it's partly, I think, the increased code size, which can lead to kind of cache misses on the code. And I think it's partly just like randomness in the runtime, which can happen based on how they measure it and what else is running at that moment. So I wouldn't read in too much into like 11 versus 12. That can just be random. But it looks like I'm not really improving things by making these changes. So what am I going to go back to here? Let's see. I'm going to go back to this solution for now. I'm going to go ahead and go back to this. So that solution didn't really work out. Now the question is, how else could I make this faster? So there are a few ways to do this. Let me think. Mrow. How can I go faster? Faster. Let's see. Well, one way I could go faster is I could actually avoid constructing the entire dictionary, and instead I could, that's an idea. Okay, so what I'm going to do, first I'm going to show you how I would do this with a doubly nested loop in a dumb way. So I'm going to save this code kind of off to the side. I open my trusty notepad. It's saved off screen. You can't see it, but it's there. Now, imagine that we step I through the list like this. And then, instead of having j start at I plus 1, we have j start at I minus 1. Or not at I minus 1, but actually at 0, and then j less than I, and then j plus plus. So now instead of having j go through all the values bigger than I, we have j go through all the indexes smaller than I. This also means we can start I at 1, because if I was starting at 0, there would be nothing before it anyway, so j would just go 0 times in this inner loop. So we start I at 1. So we do like 1 and 0, and then we do 2 and 0, and 2 and 1, and then we do, and so on. So in this example here, we would have 7 and 2, then we would have 11 and 2, then we'd have 11 and 7, then we'd have 11 and 15 and 2, then we'd have 15 and 7, then we'd have 15 and 11. So this will be very similar to our previous solution, but the advantage of this is it will actually allow us to adapt it to a more efficient linear solution. I'll show you what I'm talking about. Wrong solution. 6. Hold on. Oh, I forgot my I is not equal to j check. Wait, how can that happen? Hold on. Meow. So I got an output of 1 and 0. Oh, I also forgot to actually check that they are achieving the target. That's important. Meow. I am sometimes just a cat, honestly. I don't know how to use a computer. Meow. All right. We're going to give it a run. Bingo. All right. So you see that this is actually faster than some of these previous solutions when I was having the double nested loop. It's not as fast as the dictionary solution, but it is still faster. And I think the reason for that is that when we iterate over the elements smaller than I, those elements have already been loaded into the cache when they were visited on previous iterations of the loop. So this is really just better cache behavior. But that's not what's going to give us the advantage in our efficient solution. What we're going to do is we're actually going to start with, so let me bring up the code we had before in our efficient solution. So first we constructed our data structure, and then we went through and looked for the matching value for each value. But when we're doing this, when we're going and looking backwards, we can actually do both of these two loops at the same time. Let me show you what I'm talking about. I'm going to stick this in here. So now, each time I get to a new I figure out what the other value should be. I look up in the data structure we've constructed so far whether that value is in there. And if it is, first of all, I haven't put the current value in there yet. So if it's in there, it's going to be a distinct index. So we don't have to worry about I is not equal to j, because I only gets put into the value to index array or value to index map after we execute this, which means it's never going to return I when I look up this value in value to index. So we don't have to worry about I being equal to j. We just look up j, and j is going to include all the previous values in the array, which is exactly what we were doing down here, looking at all the previous values. And then if we found it, we return it. So this is pretty much the whole solution. Again, we cannot reach the end because there's always a solution. Let's go ahead and give this a run. Okay, it beat these 3 test cases. Let's see if it beats the others. It did. And I got down to 8 milliseconds now. That's a lot better. And you can see I'm now beating 44%. Or sorry, that's memory. I'm now beating 78% on runtime, which is really good. I can do a little better here. So you can see I use find and then I do the indexing, which means I'm actually doing the lookup twice. And that's not necessary. I can actually save the iterator that I get by doing this lookup. And then I can compare that. And then to get the value, I can just do iter second, which is the same thing as, so this iter refers to a key value pair. Iter key will be the value, which is other value. And iter value, or sorry, iter first will be the key, which is other value. And iter second will be the value, which is, in this case, value to index other value. So we get to keep both of these after we complete the lookup. So I just use iter second, which is the index, and then I return. So this is just kind of a little shortcut to use the information we already looked up instead of looking it up again. Give it a submit. We got about the same runtime, and that's not surprising because that lookup was only being done at the very end of the function anyway, only one time. So let's see, is there anything else we can optimize? I don't think so. I think we're gonna, there's probably some other small improvements we can do, but I'm gonna call this done for today. And I'm gonna wrap and I'm gonna go see my girlfriend. So it was good to see you guys. Thank you for coming to this little warm-up stream. This has been the, what problem is this again? The TwoSum problem. the TwoSum problem on LeetCode. Thanks everyone for making it, and bye for now. Meow.